Hi. All right, here we are in chapter 6. So chapter 6 is about analysis of variance, and it's in two parts. The first part is on variance tests, and the second part is on ANOVA, which is also known as analysis of variance. But that one's actually not about variance, it's about means. I'll get into more about why that is when we get to part B. Here we are in part A. So we're going to have the same Gaussian models as in chapter 2, which is for one sample, and in chapter 5 we had Gaussian models for two samples. And we'll take those in turn, but now we're doing a test of variance, so the focus is on sigma squared. Okay, so that's kind of gross. So one thing at a time. So we'll start with one sample tests. Recall from chapter 2 that the model is this one. So that's the same, but the focus now when testing is on the variance parameter. So we want to know if the variance takes on a particular value that I'll call sigma naught squared versus the alternative that it doesn't. Okay. So the models are the same as in chapter 2, so we're going to have the same simulation as chapter 2. But we'll need to use a different statistic. In chapter 2, we focused on the mean. That's mu, and we estimated the mean with y bar. Now our focus is on sigma squared, and our estimate from chapter 3 is s squared, which is actually, instead of mu hat, we can just write y bar. Okay, so that's our setup. We have the same model generation, so we're going to have the same simulation, but we're going to calculate a different statistic in that simulation. So let's pop over to R, and we'll go grab our data from, where did we do that? I think this data is from chapter 5, or I can't remember now. This is the ice cream scooping data, okay? And our estimate, s squared, I can calculate with the variance command. So that's my estimate. Suppose I want to know if sigma squared is equal to 0.5 squared. So that's my one to know. Sigma 2 is 0.5 squared. Okay? So that's my null hypothesis. This is my H naught. Okay. So to do the simulation, I need a value of mu, but it doesn't matter what I choose. This is sort of similar to chapter 2 where I needed a value of sigma squared. That does affect the outcome of the test, but in this case, the value of mu that I need to do the simulation does not affect the outcome of the test. Okay, so let's do a big simulation loop. In my notes, I did 100,000, but I don't know if that many is actually necessary. So I'm going to generate some Gaussian samples of size n, which is the same length as my data set, and I'm going to use the value of mu. I'm just going to put in 4. It doesn't really matter what you do. Pick a different number if you want to. and then I got to put in the value of sigma squared from the null hypothesis. Then I'm going to save a statistic that is my estimate of S2. So that's a var of ys. I'm going to save that statistic. This is the only line that's different from the simulation in chapter 2. And I need to make sure I save that the right way. And then I can run the simulation. Oops, I didn't run that line of code. S2S, making all sorts of mistakes here in real time for you. And then we can visualize the simulation. Okay. I don't think you can see the plot, so let me put the plot up. So there you go, you have the plot there. And then I can put on the value of the estimated statistic from the data. And to me, this looks like a rare occurrence under the null hypothesis because the statistic is way out there in the tail. And calculate the p-value in the usual way. So 2 times the mean of the samples bigger than the estimate. And so that p-value is 2.6%. That's less than the usual 5% threshold, so I'm going to reject the null hypothesis. Okay, so simulation is easy. It's just the same as chapter 2. And the p-value calculation is similar to chapter 2 also, but the calculation of the statistic is different. All right. How do we do this the math way? Okay, so I'll get myself some space here. Recall from chapter 3 that a different thing that we called V, which is n minus 1 times s squared over sigma squared, has a chi-squared distribution with n minus 1 degrees of freedom. So that's from chapter 3. So it's going to be easier to use V instead of s squared with closed form calculations. Okay, so I can straight away go over to R and start working with that. So V is S2 times n minus 1 divided by sigma 2. So that's just chapter 3. Okay, and then I can do 2 times p chi sq v n minus 1 lower tail equals false. I know that it's going to be an upper tail calculation because I already did the simulation, but if you didn't do the simulation, then you might have to check which tail of this chi-square distribution your statistic is in. Okay, and you can see that the answer is very similar to what we got by simulation. So that's a one sample variance test. How about a confidence interval? Okay, so now I want to tell you about a confidence for sigma squared. Remember how to do that with simulation. So you can either switch the order So if you're doing a sim, you can switch sigma squared and s squared in the code and then calculate quantiles. I'm actually not going to do that right now because I've left that for you in the book as a homework exercise and I don't want to give it away. Or if you want to do things the math way, you can borrow the same calculation that we did for confidence intervals in chapter 3, which we did for the mean. You can use them here for the variance. So remember how that looks. If I want a size alpha confidence interval, which might give me 95% if I choose alpha equals 0.5, I want to find the probability for some quantile on both sides. So I just take half for both sides. Okay, and then I'm going to write my statistic in. So that's n minus 1 s squared over sigma squared. And then I'm going to flip everything so that the sigma squared is in the numerator and the n minus 1 times s squared is in the denominator of those quantiles. And since I am taking reciprocals, that's going to change the order of things. I'm going to end up with s squared n minus 1 over the right-hand quantile, but it's going to be moved over to the left. And the one from the left is going to go to the right. Okay, so now I know what to calculate. So I'm just going to make a little note here. This is switched if you compare to the previous line because you're dividing an inequality. Okay, so let's go over and do that in R. We'll do a confidence interval. All right, so first I have to decide what my quantile is going to be. We know that it has that the s squared has a chi-square distribution, or sigma squared has a chi-square distribution. So Q, CHI, S, Q, with the quantiles I want are 0.025 or 2.5%, 0.975 or 97.5%, with n minus 1 degrees of freedom. And then I can take this S2 value following the formula times n minus 1 and then divide by Q. If you do it exactly following that formula, you'll notice that the interval is reversed from what it normally is. So usually we'd put the smaller one first and the bigger one second. So this is the same thing as going on when you're supposed to switch the order of the quantiles in the inequality the math way. So if you want to get it the right way around, you can just reverse these quantiles. Okay, so that's a confidence interval. And you can use this number to check your work on the homework problem to make sure you're getting the right confidence interval with your simulation. All right, so that wraps up one sample. Let's go over to 2 samples. So now we're going to do 2 samples. Okay, again, same setup as chapter 5, where we have a y sample and y of those, mu y and sigma y squared, and an x sample with similarly notated parameters. But now our interest is not in whether the means are the same or not. What we want to know is if the variances are the same versus the alternative that they're not. Okay, and this is the same as the ratio being 1. So if the two variances are the same, their ratio is 1. Remember that we know that we can estimate sigma y squared with sigma with s y squared and sigma x squared with sx squared. And if we're thinking about their ratio, sy squared over sx squared, this gives us a statistic to look at. Gives a statistic that we can use for testing. And that statistic has a particular name that I'll explain a little bit later. We'll call that f. So this is the ratio that's f. So if we go to a simulation, which we can borrow from chapter 5, and calculate variances and their ratio instead of looking at the individual variances separately, we can have a simulation-based hypothesis test. So let me show you what I mean. Okay, so we're over here in 2 samples now. So I'm going to have to create a data set that has 2 samples. So we're going to partition into sorbet and ice cream, just like we did in chapter 5. So we'll call x, those are the y's from 10 to 16. Those are the ones that we're calling sorbet. And my nx is length of x, and my s2x is var of x. And then the y's will be just the first original y values, and those are the ice cream. And my ny is length of y, and my s2y is var of y. And then my test statistic is this ratio that I'm going to call f. s2y over s2x. Now the simulation. So we just need equal sigma 2 values. Doesn't matter what. So I need to pick a value of S2 or sigma 2. I'm just going to pick one. You can choose something different. Okay, and we're going to use the mu value from earlier, which we fixed to be 4. And again, any value works. So I'm going to save f statistics. I'm going to use the value of n that I set up earlier. And then I'm going to draw y's from a Gaussian population, and y of them with mean mu and variance sigma 2. Better make sure to take the square root, although the square root of 1 is just 1, so that would work without the square root. And x's okay, notice really the only thing that matters here is ny and nx, since everything else is the same each time you do it, no matter what values of mu and sigma squared you choose. Given those virtual draws, I get an estimate of S2 ys, so that's a var of ys, and I get an S2x, which is the variance of the xs's, and then my f's are their ratio. And I think that completes the simulation. So this part of it is exactly the same as chapter 5, but instead of calculating averages, I'm calculating s-squareds for the two samples, and then I'm distilling that down into one statistic by looking at their ratio. So I think this will run unless I made a mistake. And you can do the usual visual. If you type correctly. Okay, let me reveal those plots. So this is kind of a funny looking histogram. It has a really heavy right-hand tail because every once in a while you get a large numerator, a large S2YX, and a small denominator, a small S2XS, and that gives you a very large F value. I like to focus this histogram on the part of it that really has some shape, which in this case is going to be between 0 and 8. In fact, it's always going to be in that range, but you have to also change this part of it to show just the part of the histogram that's less than 8. Okay, so that's a nicer histogram to look at. Remember, this is just a visual, so what you look at is up to you. The final p-value calculation is going to be using the entire histogram, no matter what you choose to visualize. So let's put the value of the statistic on there. Oops, not S, F. Okay, there's that value of the statistic. To me, it looks like we're not going to be able to reject this null hypothesis because this value of the statistic is not very far into the tail, but I can calculate a p-value. So 2 times pf, oh, I'm sorry, I'm going ahead of myself. 2 times mean of fs greater than f. So that's 27%, so not enough evidence to reject the null hypothesis. All right, the math way. Let's go back to the whiteboard and scroll to give us some more space. All right, so in chapter 3, we saw that S values have a chi-squared distribution with n minus 1 degrees of freedom around their sigma squareds with sort of a setup like that. So we can just write that for y's, and also for x's, right? And we can use that these two things are equal. Oops. We're assuming the null hypothesis is assuming that sigma y squared is equal to sigma x squared. So the ratio is going to have some cancellation. We'll have the chi-squared ny minus 1 over ny minus 1, and then the chi-squared nx minus 1 over nx minus 1. And the sigma y's and sigma x's cancel because they equal each other. This thing is called an F statistic, and it can be shown. I'm not going to show you because that's not easy to do. You can take that as a definition if you want, that a ratio of chi-squared random variables has a distribution called F, which is notated by the two parameters nx minus 1 and ny minus 1 as their degrees of freedom. So we can use an F distribution to calculate this test. Let me show you what I mean. The math way. So I can do 2 times PF and give it the F and NY minus 1 and NX minus 1, and I need to make sure I do lower tail equals false. Anytime you get a p-value is supposed to be a probability, so if you're getting a number bigger than 1, you're doing it wrong. So I know I did something wrong here. I have to tell it lower tail equals false, because I can see in my histogram, which I'll put back up there, I can see that my statistic is in the right tail. So I need to do my integration into the right tail. So there we go. So here I calculate the math way, 0.271, and when I do it by simulation, I get 0.269. So they're the same up to 2 significant digits. All right, that's the first half of chapter 6.